This is an introduction to Unit 1 transformations for Math 30 Pure. And today, or this lesson, we're going to look at some of the basic functions or basic graphs that we work with in this unit. This unit really is about transforming graphs, stretching graphs, reflecting graphs, doing all these things to regular graphs that you likely would never have imagined. But it's nice to have a foundation of some of the very fundamental basic graphs that we work with, which are mostly covered in Math 10, Math 20, and equivalent courses around the place. So here are some of the basic functions. The first one is the linear graph, the linear function or the linear relation. And it is a form, typically, y is equal to mx plus b. Now this is referred to as the slope y-intercept method. I don't have the best writing, but hopefully you can make sense of this. Slope y-intercept form, I should say. And your m value is the slope of the graph, of the line, and the b value is the y-intercept. Really important graph for all sorts of applications. We don't really work with it that much here, actually, in 30 Pure. However, if you're taking any sort of physics course, or if you're taking Math 31, it becomes a really big deal. This would be a typical example. Y is equal to negative 2/3 x plus 1. So just by inspection of this equation, we know that the slope, m, is equal to negative 2/3. Now I'm not going to really dwell on the nature of slope too much, but this graph would be falling as you go from left to right. And then the plus 1 is the y-intercept. So it crosses the y-axis at y is equal to 1. And we will see that shortly. Very helpful. You'll notice that the y is always isolated in these cases. Here's another one. Negative 2x plus 4y minus 6 is equal to 0. This is often referred to as the standard or general form. And if you wanted to get more information on it, you would isolate the y, which is what we can do, and I will do right now. So most of you would have seen this before. If you keep the y where it is, algebraically, you can take that negative 2x to the other side, where it becomes positive 2x. You can add 6 on to both sides. And then when you divide by 4, you'll get y is equal to 2x over 4, or 2 over 4x, plus 6 over 4. Remember, with these video lessons, it's on a player, a media player, so you can pause, you can stop, you can do the question yourself, and then return to the answer, which is really a recommended approach if it's something you can handle. So if I'm going too fast, feel free to pause me at any time. You can't do that in a regular class, unfortunately. So when I get this thing reduced, by reducing that fraction 2 over 4 and then 6 over 4, I get this. So this gives me the graph in slope y-intercept form. Now I can do something with it if I wanted to. Now this is our first graph. Take a look at it. It does have a y-intercept of 1. The x-intercept we don't know. We'd have to isolate or replace y with 0 and then isolate the x. And you know, if you really want to look at this closely, it's maybe a little tough to tell, but the slope value is 2 across and then 3 down. So if you didn't really do a good job of seeing that on this particular graph, but that's what it would mean. The ratio of rise over run is 2 over 3. So once again, not a big deal for us, but slope is always equal to rise over run. Sure you know that. So it's telling you how much the graph is changing vertically as opposed to how much it's changing horizontally. So it's a measure of the line's steepness. This other graph, the second one, would look like this. It would have been easier to see if the y had been isolated, and if you recall that it was equal to y is equal to 1/2 x plus 3 over 2. And that makes sense because the y-intercept is at 3 over 2. You can tell that. The slope 1/2, well, a little tough to tell off this graph, but in fact, if you did find points that you could work with, it would be rising at the rate of 1 unit up for 2 units across, all the way through. So you can amuse yourself with linear graphs for a long time. Unfortunately, we need to move on. And a very common graph is the quadratic function, and this one you will work a lot with. It's an old Math 20 topic as well, so had you come through the system recently, you would have been exposed to quadratic functions. And they're of form y is equal to x squared in their simplest form. A lot of the times they'll write them as y is equal to ax squared. When we get into the transformations proper, then we will flesh out that form quite a bit. But here's a few examples. Now this is a more complicated one. Y is equal to negative 2 x plus 1 squared minus 1, the type of thing we'll be looking at in a week or so. But really what matters is that the variable x is squared, and then we have y is equal to x squared. Soon we'll be graphing these on our calculator, so you'll get another crack at them, or a faster way to graph them. But stuff like this, most of you will be comfortable graphing by hand. If you're not already, you will be soon. Here's another one, 1/2 5x squared. And here we have the x squared once again. That's what matters. This time it's using function notation, f at x, but that is the same thing as y equal to. And here's your basic y is equal to x squared. The shape itself is referred to as a parabola, and we spend a lot of time working with parabolas in this course. And those other numbers simply transform it. They move it around, they flip it over, they do all sorts of weird things. Now, the absolute value function you also would have probably seen sometime. And its form is y is equal to, or f at x, I'm using function notation in this case, is equal to the absolute value of x. And the nature of this sort of thing is that this symbol absolute value, which is just these two vertical lines, simply make everything positive. And it's on your graphing calculator. You can find it as, and I will be graphing these all the time. I don't know what your comfort level is, but ABS and then X, close bracket. I usually get this in my catalog, but I will be going through all of this soon, so I wouldn't worry about it too much. Mostly it's mostly it's recognition. And you see this is another absolute value function, negative 3, multiplied by the absolute value of x plus 2. And the basic absolute value graph just looks like a V with its vertex right there at the origin. But we can do lots with it by transforming that graph. Now, the next one, so I'm going through these ones fairly quickly. I'm expecting you just to look at them and read them and go through. There's really no homework attached to this lesson, and just get comfortable with the shapes because they're going to start appearing in context fairly soon. Square root functions are y is equal to the square root of x, or f at x equal root x. And for example, a more complicated one, y is equal to the square root of x plus 2 plus 1. And so we've taken the basic square root graph and we've transformed it. And that's what we'll be doing in this unit. This is what it looks like on its own. It's really half of a parabola that's opening up to the right for your information. And that becomes an issue for us later on. Note that this is the positive square root of x. If it was the negative square root of x, it would be below the x-axis. Reciprocal function, one of the more complicated ones. These ones are always of this form, f at x or y is equal to 1 over x. You'll notice that I have stated that x cannot be equal to 0. You cannot have 0 on the denominator. You do not divide by 0. So you get it in this form. And the nature of the graph, well, first off, let's take a look at a few examples of it. This, too, is a reciprocal function, negative 1 over x plus 3. So it's a regular graph, but it's been transformed. Here's another one. F at x is equal to 2 over x minus 5. As long as we've got that x on the denominator, we know we're dealing with a reciprocal function. This is what y is equal to 1 over x looks like. So you can see that it does not touch the y-axis. The y-axis, in this case, is a vertical asymptote. That's the word. Just like the x-axis is a horizontal. Type of thing you can do. Those words, or that word asymptote, will be coming back often in the next few units. Not much more we can do with that one. And finally, the exponential function, which is so important that it has an entire unit named after it, which we'll get to in Unit 3. And this one is a form y is equal to a times b to the x. Now, I put this a in here just because it's quite significant. What matters most is that the x is in the exponent. That's the nature of an exponential function. And we have a few things to be aware of. I don't know why this is written so large here, because it's important, I guess. The base b has to be greater than 0, and b cannot be equal to 1. Don't worry about that yet. As I said, it has a unit dedicated to this function, so then we really we care a lot then. But this is what it looks like. Y is equal to 3 to the exponent of x. Could have y is equal to 2 times 1/5 to the x. But the key is that the x variable, or whichever variable is used for x, is going to be in the exponent. And then y is a function of that value. And here's a very standard exponential function with the y-intercept of 1, which, by the way, we would expect, because if you did solve for the y-intercept, you replace x with 0. So let me call that your y-intercept. And as I hope you remember, anything to the exponent of 0 is just equal to 1. So your exponential function should have a y-intercept of 1. And there is no x-intercept. You can kind of tell from this graph, because the x-axis is a horizontal asymptote. Sort of thing you can do. Now that takes care of this topic. The next lesson we'll do another review topic. So the first few lessons are working on stuff that you have seen before, and then in about the third or fourth day there will be actually looking at stuff that might strike you as being a little bit new. Thank you for your time.